Okay, this video, I'm going to warn you up front, is one of the more challenging things to understand because some numbers will look slightly different than what you're used to, and it's hard to make the conceptual connection sometimes between what they look like and what they mean. So I'm going to walk through pH and the meaning behind it, and I'm going to give you some things you can work with in your next assignment that you don't really need a calculator for. I'm intentionally making it things you can estimate in your head so that you get the meaning of this down as opposed to just punch something into a calculator and really hope for the best. I want you to be able to understand as much as possible about what's going on. Okay, so we're going to take a look at pH, and most people have heard of this scale. So I wrote it over here. This is the pH scale. It goes basically from 0 to 14. Now that's not totally true, but for all practical purposes, for things that we see in nature, solutions that you come across in nature, they tend to be really, really diluted. Okay, most of the things you run into in everyday life are mostly water and just little bits of acids or bases within them. So this scale was made to be able to communicate that between people, okay? Because these numbers get so complicated looking. They're really not, but they're so diluted. The concentrations of hydrogens or hydroxides in most things are so low that you get really tiny numbers with lots of zeros after a decimal, and it gets hard to communicate them. So this is a compressed scale to try to be able to communicate it easier. Okay, but when you're getting accustomed to it, it's not really that easy at all. So the way I try to relate this to students is through earthquakes. Okay, if you've ever been in an earthquake, and many of you haven't, but if you have something to kind of base your ideas on. Like, this is about how big something feels. But earthquakes have these huge ranges of magnitudes. And so we have a scale called the Richter scale that operates a lot like this pH scale. It's compressed, okay? So if you were in a 5.0 earthquake and you knew what that felt like, and then you were to experience a 6.0 earthquake, 6.0 on the Richter scale is really 10 times as strong as a 5.0. So each jump between these numbers is really a factor of 10 times the magnitude. If you were to experience a 7.0 earthquake, it is going to be 100 times more powerful than a 5.0. So each jump gives you another multiplying factor of 10. And that's kind of hard to visualize for most people. These numbers get so big that the scale has been compressed to these simple whole numbers right here. So someone can look at a number and say, oh, I was in a 6.2 earthquake, and not realize that that's 10 times as strong as a 5.2 earthquake. Okay? So it's called a logarithmic scale, and those of you who get into logarithms in algebra, this is where they're used. Okay, it's hard to sometimes see the use of them while you're dealing with them mechanically. Now, the pH scale is similar, only it's reversed in that the scale kind of goes down from 14 to 7 to 0. Okay, what I mean by that is if something has a pH of 3, it's pretty diluted. We're going to learn about how diluted that is in just a moment. But if you had something that had a pH of 2, it's actually more acidic. The further away from 7 you get, the further down the scale, the more acidic something is. The further up from 7 you get, the more basic it is. And what that really means is a pH of 2 is actually 10 times as concentrated. And when I say it's concentrated, I mean it has 10 times the amount of hydrogen ions floating around in solution. If you had a pH of 1, it has 100 times the amount of hydrogens floating around in solution. And there's such a vast difference in concentrations of things we run into in everyday life that these numbers that are way different than each other get compressed into a logarithmic scale where we deal with small values. So someone looks at measures a solution and it's got a pH of 2. Well, that just means it's 10 times as concentrated as something that had a pH of 3. And each digit you move goes another factor of 10. So it'd be 10 times, 100 times, 1,000 times, and so on. Now, this can really get out of control quick, all right? So we're going to deal with pHs in this lesson that all come out to be nice whole numbers. We're not going to deal with a pH of 2.7. We're going to deal with pH of 2 or pH of 3. And the purpose behind that is so that you can do this in your head and recognize the patterns without relying on a calculator, and that hopefully will help us hang on to some of the meaning here. Okay, now, There's a whole bunch of ways to relate things. And basically, I've put down 4 different measurements of an acid or a base, and all 4 of these measurements are accurate. Okay? You see these little brackets? Those brackets are another way of saying molarity. Okay, it's just a shorthand version in chemistry of saying this is a concentration. It's the molarity of hydrogen. Basically, how many hydrogen ions are floating around in solution. Okay, pH directly reflects that amount. Okay. Now over here we have OH. Those are prevalent in bases. Okay, and this means the molarity of the hydroxide ion. And we have this value called a pOH that reflects that hydroxide molarity. And you start to have your mind spin a little bit on what do all these things mean, but each one of these measurements, so to speak, can be kind of interpreted by itself or compared to something else, and you can tell a lot about an acid or a base or some unknown substance just based on one of these measurements. Okay? So what I'm going to do is I'm going to walk you through the relationship here, and then we'll look at why we use one particular one instead of another one. Now, I want to look back at these things down here. Okay, pH of 1, a pH of 2, and a pH of 3. I want to give you some values to start kind of grasping and hanging on to. A pH of 1 means that this solution has a hydrogen molarity of 0.1 molar. This right here, a pH of 2, means it has a hydrogen molarity of 0.01 molar. Okay, now you're going to start to pick up on a pattern here. A pH of 3 means it has a hydrogen molarity of 0.001 molar. Now you notice that each time we go up 1 unit, we get 10 times smaller here. It's like moving the decimal 1 spot, which is a factor of 10. This is 10 times more diluted than this is. This is 100 times more diluted than this is. But how can we do these numbers and relate them to a pH value easily? And the answer to that is to use scientific notation. If I were to take this number and write it in scientific notation, I would move my decimal 1, 2, 3 spots back, and this would be 1 times 10 to the minus third molar. Notice that exponent right there matches the pH. If I move this back 1, 2 spots, it's 1 times 10 to the minus second molar. If I move this back, it's 1 times 10 to the minus first molar. Now that negative exponent means we have a really tiny number here, something smaller than 1. The exponent itself, the number there, tells you how many places you would move the decimal. Okay, it's real easy to get this confused, so it's going to take some practice. I know that. Okay, what I want you to remind yourself about constantly is this number right here is a lot smaller than this number right here. This one is the bigger one. And that's oftentimes lost in this because 1 looks like it should be smaller than 3, but when we're dealing with negative exponents, this is actually 100 times bigger than this value is. So it can easily get lost. What I'm going to do is I'm going to show you the relationship between the molarities and the pH values and how you can convert pH and pOH between one or the other. And then we'll see if we can make some sense of all this, okay? So if you look at this chart, this represents an unknown solution, solution 1, and I have one single measurement for this solution. What I'm going to do is fill in all the other measurements and all the other characteristics just based on this one thing. This tells me the hydrogen amount is 1 times 10 to the minus third. Well, I know that that is going to tell me that the pH is going to be 3. All right? Now, that's an acid. Okay, that's an acid because it has a pH level. I look at this, and pH of 3 is going to end up right here. It's going to be on the acid side of that scale. So this is an acid. Okay, I know that. However, because it's dissolved in water, there's still going to be some hydroxide ions floating around. Not very many. The more hydrogens you have, the less hydroxides there will be. It's this thing called equilibrium where one goes up, the other goes down, but there's always going to be a few of each. And we can analyze this pretty easy just with some mental math here. So if the pH is 3, look down here. This is a nice equation to get used to. the pH and the pOH added together are always going to equal 14. So if the pH is 3, the pOH here must be 11, because 11 plus 3 would give me 14. And then I know I can see the same pattern exists here. If the pOH is 11, that must mean that the hydroxide molarity was 1 times 10 to the minus 11. Now, I want you to pause for a second, and there's a whole bunch of numbers here. Which one of these two concentrations is bigger? Well, that would be this. It's deceptive, but that is a bigger value. Okay, it's thousands and thousands of times bigger than 1 times 10 to the minus 11. This is like 0.000 with 10 zeros and then a 1. It's a really, really small amount. So there's a tiny amount of hydroxides and lots of hydrogens in comparison. More hydrogens means I have an acid. Okay. Now, let's take a look at this one down here. We've been given one value right here, the hydroxide molarity. So I'm going to look at what that could give me. If I know the molarity of this ion, I can find the pOH just by looking at this exponent. The pOH is going to be 2. Now I'm going to look down here and go, okay, if the pOH is 2, what does the pH have to be for this whole thing to equal 14? And that's going to end up being 12. 12 plus 2 gives me 14. And now I know if the pH is 12, I can work my way backwards with this same relationship. This will be 1 times 10 to the minus 12th. Now take a look at where we're at. Okay, this is a tiny number. This is a much larger number. I have lots of hydroxides, very few hydrogens. So that means I must have a lot more hydroxides. It's going to be a base. Now that kind of analysis is not really normal for most people. Okay, a lot of people who haven't been through chemistry or have forgotten about it would never be able to follow that. So in common practice, this scale, there's all 4 of these measurements tell the same story. Okay, we had to pick one to communicate with most people. And that one we're going to pick is the pH scale. That's just been chosen. We could have easily used the pOH scale, but nobody's heard of it. Everybody uses the pH scale. So we're going to always go back to this measurement here, even though all 4 of them are essentially saying the same thing. The pH here is 3, that means it's an acid. The pH here is 12, it means it's a base. If it's above 7, it's a base. If it's below 7, it's an acid. If it's right on 7, it's neutral. Okay, so this is our first kind of step in being able to interpret. In your homework, I'm going to give you some of these things where I give you one piece of information. I want you to try to fill in all the rest, just so you get accustomed to going back and forth between these values and hopefully kind of absorb some of the meaning behind them, because it's really easy to lose. In the next video I'm going to post about this, we'll go through and estimate one from scratch from some like measurements we would have in a lab. This right here, though, is just to get you used to what does pH actually mean and what can these different measurements show you. Okay?